Hello, welcome back to the series on professional development skills for engineers. After giving the 3 talks on preparing, planning, and delivering a great oral presentation, I want to give a little bit of an example. So I'm going to start about today talking about how you organize the introduction to your talk with a technique I refer to as the funnel. Then I'll give a little brief example. So the introduction is key. The introduction sets the stage for the rest of your talk. In those first couple minutes, you can easily capture the attention of the audience, or you can lose them completely. If you lose them completely in the first couple of minutes of your talk, they're done and they're not coming back. So how do you really set the stage well and capture their attention and then hold it for the rest of the time? So as I mentioned previously, I'm teaching the honors undergraduates here in the department as they work on undergraduate research theses, as well as my grad students and other committees here in the department. Throughout that, I've seen that it's really the introduction where students tend to struggle the most, particularly if they're starting off on research. As with the introduction, students know very well that what they are going to do. They have a good sense of what they're going to build, what they're going to make, what data they're going to collect, what simulations they're going to run, and those sorts of things. But they don't really know why they're going to do it. Now, when I started graduate school, my advisor sent me out to read a whole bunch of papers, write summaries of those papers, and then ask questions as to what was this paper doing, why this technique over the other technique, all that kind of stuff. I was reading a lot and reading for months. And at the time, I was getting really angry because I thought I wasn't doing anything. I thought he was sort of just giving me the runaround because I wanted to do research. I wanted to get in the lab, take data, build something, run a computer simulation, write some code. That I thought was research. In retrospect, it was absolutely the best thing for me because knowing what to do is the hardest thing out there. Knowing how to do it's pretty easy. I want to write this code, collect that data, that's all easy. Knowing what to do in the sense I need to know what question I want to ask and why I'm going to do that, that's really hard. So if you can get good at the skill of identifying where the hole is in the literature, asking the right question, going about and solving it, that gets to be pretty easy. So how do we start? We start by giving some background information about the topic at hand, but then there's some sort of problem, some unanswered thing, some unsettled thing in the world that needs to be solved. Because there's this unsettled thing in the world that needs to be solved, you have taken a bunch of approaches, other people in the lab have taken approaches, the field as a whole has taken a bunch of different approaches, none of which are solved. Therefore, you have a specific purpose of your work. So you'll say explicitly the purpose of your work is to X, or you hypothesize that A is greater than B. Now, in terms of a diagram, it looks like a funnel. So you start off with some general background information. You start off fairly broad at the top. Then you get a little more narrow about the facts and the data about the problem at hand. But as you get more and more narrow, you identify some shortcomings with the existing approaches, or possible alternatives, or some unsettled knowledge in the world. Then you get down very specific at the end as to what the specific task or specific purpose is that you are going to do. Now, this funnel might look familiar because if you watch the video about how to do a scientific abstract, it's the top half of how to do a scientific abstract. You start off general at the top, narrow in, specific shortcomings, and then you get to your specific purpose. With an abstract, you then stay narrow and flare back out at the end. It's typically this piece at the top, and how you funnel down from the narrow to the specific in the introduction is where people tend to lose their audience. So what I'm going to try to do is give a little bit of a practice talk about the in vivo passive kinematics of osteoarthritic knees before and after a total knee arthroplasty. This is a talk that was actually part of my PhD dissertation that I've updated a little bit here. And hopefully you'll be able to see the funnel, how I go from general to specific and end the introduction with a very specific questions to what I'm going to do. So let's start at the knee. Here's your knee. The knee is this material here, and that shiny white stuff in the middle is articular cartilage. Now this is a normal healthy knee, but when you have osteoarthritis, the nice shiny smooth white cartilage in your knee gets replaced by direct bone-on-bone contact, but the cartilage has degraded away, and even off on the side you might have some bony spurs that kind of rub up against the side of your joint. Now, osteoarthritis and other rheumatic conditions are the leading cause of disability in the United States. Back in 2003, estimated 45.8 million adults, or about 26.1% of the population, had doctor-diagnosed arthritis. As the baby boomers get older, this is going to jump to about 25% of the population, or about 67 million people in the United States will have doctor-diagnosed osteoarthritis. So a total knee arthroplasty, or total knee replacement, takes that direct bone-on-bone contact, which would be quite painful, and replaces it with a cobalt chromium and ultra-high molecular polyethylene insert. Now, a TKA successfully treats the pain, disability, and loss of motion due to osteoarthritis. This is quite common. As of a couple years ago, there are over 750,000 performed in the United States every year. Again, as these baby boomers get older, by the time we get to 2030, there'll be approximately between 3.5 and 4.3 million total knee arthroplasties performed per year in the United States alone. Now, the outcomes, in some senses, are pretty good. Long-term survival rates are quite good, between 90 and 95% for elderly patients. These outcomes are worse for younger, more active patients. Particularly, there is need for improvements in physical activities that are important to someone's quality of life, such as squatting, kneeling, guarding, or other recreational activities. Now, the patients following a total knee arthroplasty have challenges that are not seen in age-matched controls. They tend to walk more slowly, and their quadriceps tend to be weaker. Now, if we try to put these outcomes on a scale, where a success is any improvement over the pre-op condition and a failure is a revision or a repeat surgery, we have this nice spectrum here. Now, beforehand you might have this direct bone-on-bone contact, but patients might think after getting a surgery they want to be Usain Bolt. They want to be this stellar athlete, tip-top peak condition. But in reality, they just want to have a normal and healthy life. Maybe not as good as Usain Bolt, but still pretty good. Unfortunately, there are a lot of these suboptimal outcomes. So there's some research has suggested that up to 50% of total knee arthroplasty patients cannot climb stairs post-operatively following surgery. As you can imagine, this has a great impact on their quality of life and be able to be independent in the community. So what we want to know is, can we identify factors within the surgeon's control that can account for this range of post-operative outcomes? One of the things that the surgeon can check inside the operating room are the kinematics after total knee arthroplasty, passively. So while a total knee arthroplasty can restore alignment in the frontal plane from this bone-on-bone contact to a more straight line, the kinematics of the knees, or how the knee moves following surgery, is different from normal knees and can even be different from the design expectations of what the implant manufacturer. Previous research has also shown that the preoperative range of motion, or how much you can flex and extend your knee prior to surgery, is a good determining factor for how much you can move your knee after surgery. However, little is known about the three-dimensional kinematics of someone with an advanced osteoarthritis of the knee, and how these kinematics change from immediately before you put in the implant to immediately after you put in the implant remained unknown before we did this study. And we view this as a challenge in surgical technique. So currently how surgical technique is done and surgical practice is done, that pre-operatively you have an x-ray, then something magic happens inside the operating room. It's very much a black box that's not very rigorously or objectively recorded. And then they try to relate what they think the surgeon did inside the operating room to how someone moves on an post-operatively and how they are viewed on x-ray post-operatively. As an engineer, this was not very satisfying to me. Even some of the research in a total knee arthroplasty, maybe in the gait analysis lab, for example, preoperatively, still has this black box intraoperatively. So what people try to do, they still try to figure out what was done intraoperatively and try to relate that to post-operative outcomes, or just hook up and around what happened in surgery, try to relate directly the pre-op condition to the post-op condition. But what we want to try to do here at Ohio State is, instead of making this a black box, let's make it a gray box, because we're scarlet and gray, so that's why it's a gray box. So we can make measurements of surgical technique inside of the operating room. Then we can integrate the pre-op, the intra-op, and the post-operative conditions with some preoperative planning, some post-operative analysis, some computer simulations, so that in the future we can feed this information back to the surgeon to identify, here's some good areas for surgical technique, how ligaments should be balanced, how the components should be aligned. If you do this, people will have good outcomes. If you do that, they'll have bad outcomes. Do more of this to have good outcomes and do less of that. So this is the long-term goal that we're striving towards. So in this first study, what we wanted to know, we wanted to ask two specific questions. We want to know, are the passive kinematics as measured inside the operating room of advanced arthritic knees are they different from normal and healthy knees? And does a total knee arthroplasty restore these passive knee kinematics towards normal? And what we thought was that this, at the time, was the first ever intraoperative characterization of knee kinematics before and after a total knee arthroplasty, and there's a reference to the paper there down at the bottom. So what I would do then at this point, I would then proceed forward with what my methodology would be. So my methodology would be, we had 17 patients with advanced osteoarthritis, here are all the details about them, and I would launch into the rest of my talk as to where I got the patients, where I got the cadavers, and all that other thing. Then I would go through slides of here, more of my methods, my results, all that sort of stuff. But that last slide about the questions I ask, that's a pretty important question slide or purpose slide, because what I can do at the end, I can come back to it. I mentioned in one of the previous talks on how I had a speaker come up to me that I asked a question that actually answered it at the end, and no one tends to do that. Well, here's how I answered it. I asked this one question: are the passive kinematics of osteoarthritic knees different from normal healthy knees? In fact, yes, they are. There's different varus valgus motions and a loss of screw home motion, but sometimes no, they're not, because they have normal anterior and posterior motion. Does a total knee restore knee kinematics towards normal? Yes, it corrects deformity, improves varus valgus rotations, but no, it reduces a screw home motion and introduces abnormal femoral anterior translation. Now, if these results are interesting to you, I gave you the reference to the paper, so definitely go back and check out what our paper is and what we did. But because I set it up well at the beginning, and I had this clear purpose at the end, I can come back to that later on in the talk. If you have a much longer talk, this is only about a 12-minute talk, if you have a much longer talk, you have many purposes, you can bring that purpose slide back multiple times throughout the talk and give short little summaries as you go. But the ability to easily set up that talk at the beginning with asking specific hypotheses or specific purposes allows you to come back, summarize it clearly, and answer those questions and those hypotheses at the end, like what I did here. At the end, you also show your acknowledgement slides. Here's an example of an acknowledgement slide I had when I first started here at Ohio State. I had a whole bunch of people helping me at both at Stanford, at Penn State, at Pittsburgh, and then again at Ohio State, and some of the funding that helped us to do it. So this was, you start off your talk with a funnel, use the funnel, start off broad, go narrow, and then end narrow with a specific purpose, a specific hypothesis. Hope you enjoyed my little quick introduction there for you. Want to know more, go read the paper. Hopefully this was a great example for you to help you get going and giving a great technical talk.